Good morning, everyone. Yesterday, a lot of keynote speakers mentioned that OCP is going to invest more on the software side. So here you go today. We have this AI hardware software co-design. So my name is Weifeng. I'm representing this AI co-design work group to report the progress we made in this maybe more than 6 months of this year. So first of all, I'd like to thank all the members in this work group, especially very talented group of people, and also with a strong support from Alicia and Alan. We'd like to thank two of you very much for the strong support for this work group. So what we want to talk about here is the future AI hardware software co-design. Future means we are not exactly looking to the existing problem people are solving right now, because there's no need for us to invest more time to do the exactly same thing. So what we want to look at is like next maybe 2 or 3 years or even 5 years beyond, exactly what AI application may look like, and from hardware software co-design point of view, what we need to do in order for us to really speed up this co-design. So in order for us to get into this problem, so the whole group spent lots of time trying to identify what the future AI application may look like. So that means we want to solve this instead of just directly get into, let's say, hardware architectures and software frameworks. And we want to look at it from applications perspective, exactly what do we need, so that we can work backwards to see what type of architecture may be suitable for future AI applications. So we made after we did a lot of background study, lots of discussion within the group, and we reached a claim here. So we believe that future AI application is still lots of uncertainty here. And because both AI algorithms and AI acceleration architectures are still evolving very fast. So then based upon this observation, then we made an assumption that future-oriented AI co-design is necessarily of spatial and temporal scalability. Maybe I'll just explain a little bit here what is the temporal and the spatial scalability. When we talk about this scalability, certainly we want to scale out our AI computation power, right? And we do lots of design trying to add more resource to our architecture so that we can try to scale out this AI computation either linearly with the resource or trying to maybe even bit more slow. The temporal, that's called like a spatial scalability. The temporal scalability means we are not only targeting existing algorithm, and our architecture can be adaptively solve the problem for the future. So that means we add a new dimension to our existing co-design, not just looking for the architectural application alone. We actually add a new dimension. Instead of just spatial scalability, we add a new dimension called temporal scalability. So our future architecture, by co-design, we are able to scale in the computation power, performance power, whatever the dimension we are defined now. On the top of this, we add this temporal scalability so that our architecture can self-adaptive for the future. So this basically is the claim the group made for this co-design. So this is basically the main theme of the group. So based upon this claim, we made a charter for the work group. The first thing is we want to characterize the critical features for future AI applications. And as we know that current research actually already have published results like future AI applications likely it's going to be compositional model and could be trillions of parameters and dealing with petascale of data. All of this will have great impact on our future architecture and overall cost when we run in AI applications. And we also want to identify the architecture innovations, for example, the novel architectures, interconnect, and configurability to enable so-called high-performance polymorphic computing. So in this afternoon's breakout session, we are going to present the details exactly we call it polymorphic architecture for future AI applications. So we'll welcome everyone to attend that breakout session, and we'll explain the details exactly what we are trying to do here. And based upon these two critical tasks, and then the work group also work on the co-design ideas based upon the hardware simulation and software tooling as well. And then we build collaboration between the industry and the academia to prototype the co-design. So this is the overall group charter. And we also made a list of deliverables for the work group. And the first deliverable is a white paper or research paper. And the second one is architecture and system prototyping. So that means we are going to prototype, compute, and interconnect architecture, and which has that two dimensions I mentioned, spatial scalability and temporal scalability. And we also build like a system level simulation, trying to see from hardware and software perspective exactly how do we actually solve those key issues we defined before. And based upon this simulation, we also want to benchmark this prototype with one use case. Right now, we haven't really settled down exactly which use case. Very likely, it's going to be like large model based on large model training. Just want to give you an idea what type of prototype of this hardware software co-design architecture we are looking at. And here we define architectural composability for the polymorphism. Basically, as I mentioned that we are talking about these two dimensions of scalability, and we imagine that our future co-design is based upon the polymorphism to solve that future AI application, because AI application is still evolving. So this is more like a moving target. And the critical feature for this co-design is the architectural composability for future AI. And this is based upon some of the ongoing research like composability, the neurocompositional computing. I do have reference for this, but just because of time, I'm not going to show that. But in case people are interested in this, then we can talk offline. And another critical feature for this co-design is we call it just-in-time configurability for future computing functors. And just-in-time means we can just make instantly adapt our architecture just for your application. Typically, people know that for general-purpose application, the performance or the efficiency is definitely not perfect, right? So we want to build like a domain-specific architectures to solve a specific problem. So here we have the just-in-time configurability to make sure that our architecture, although it may look like a general purpose, but can instantly adapt to whatever your application. So this we call the just-in-time configurability for computing functors and interconnect. And also, we are able to compute the computation task according to the new polymorphic architecture. So that means after reconfigured architecture, and we are able to tailor our application, partition all the subtasks, exactly map this subtask to the new architecture, so that we get the best efficiency. So here I just want to give a brief overview about this overall architecture. And we'll certainly provide more details in our breakout session. And first of all, we basically want to make sure our architecture is able to have a fine-grained composability and all the way to coarse-grained composability. That means our architecture can be adaptive to any type of applications, and from general purpose to some domain-specific application. And at each of this level, and we can basically scale up this from, let's say, compute pod level to compute nodes to compute unit and to chiplets, and then all the way to fine-grained, like coarse-grained reconfigurable architectural chiplets. The rationale behind this is we believe that a future AI application is based upon neurocompositional functions, and our architecture based upon this type of design is align well with this compositionally structured nature of future AI. Second, from a technologist perspective, and people are building this high-performance chiplet-based heterogeneous computing. Right? This actually is ongoing, and there was lots of a very active area, not only in the research but also in the practice in the industry. And the second element for this technology is based upon the high, ultra-low latency for the interconnect technology. For example, like optic, maybe some other advanced interconnect technology. And I know that there's like industry, a new industry consortia like UCIe. They actually work on this kind of a chiplet level of interconnect. There's certainly the bandwidth and latency will be dramatically improved over previous generations. The configurability is key to enable this polymorphism and reconfigurability, and certainly we don't want to take, let's say, days or hours, to reconfigure our architecture. That's actually not practical. So right now, at least there's a research, people can build in this like a prediction models, or based upon some level of like a trained like an AI reference inference model, so that you can actually, according to your subtask and the mapping of the topology of your architecture, they are able to immediately generate like efficient map between the task and the actual architecture. So this can be done in the tens of cycles. So this actually makes this just-in-time configurability practical. So based upon all those studies and also the discussions and the chart of the group, we do made some progress towards this goal. The first one is we identify the critical components of AI co-design, and we define, we study detailed problems in each of these domains in terms of a compute, interconnect, memory and storage, and AI software ecosystem. And we also identified ideas to enable spatial and temporal scalability, and this so-called polymorphic architecture for future AI ML applications. So this is exactly the topic we are going to discuss in our breakout session. Oh, by the way, I want to just want to show. I didn't make a separate slides for this, but our breakout session is going to be first is the talk about this polymorphism architecture, followed by a panel discussion, and which is moderated by Alan Kendall from HPC sub project. He's the lead of HPC sub project. And the second progress I want to show is we are actually building the POCs. So we are working with the members of this group, like Keysight and Scalar Computing. They have network simulators, and we are also studying how to plug in our composable compute unit into the simulator. So there's a few, in order really for us to do this level of simulation, there's a few critical functions or features we need to work out, like just-in-time configurability. How do we actually do that based upon the current network simulator? And because if we want to really scale up our architecture from fine-grained composability to really coarse-grained composability, there'll be like many levels of nested network simulation for composability. This could be another challenge for this existing network simulator. So that's also something we are investigating with the members. And next one is a heterogeneous compute functors for multi-grained ISA. Certainly, if we want to scale up the granularity of the compute, the multi-grained ISA is critical for that architecture as well. At the same time, we also work on the white paper for this future AI hardware software co-design. Currently, we already have a few members participating in the writing, and overall, it's still in the drafting stage. So that's all I want to report to progress of this work group. Any questions?
Any questions?
Okay, if not, I'm done. Oh.
So you did mention that you have memory and interconnect, but is there a specific work going on in the memory area? Since we are, of course, now just working on the memory side, I want to make sure that we have good collaboration and help chime in?
Yes, certainly. Actually, when I look at your presentation, I feel like there was a lot of synergy between these two work groups.
Yes.
And especially, when we're trying to do the interconnect, we can focus in on the compute, like let's say computer unit, like GPUs, DSAs, right? That's for compute. Certainly, memory is an important part of this overall architecture. And when we see just-in-time configurability, not just for the compute resource, also means memory, like different hierarchical memories. I do feel like you mentioned like memory pooling and trying to reconfigure this memory just to adapt this new computer topology. That's actually critical for us.
Thank you. We look forward to that.
Yeah. Anything else?
So if you're interested in this work stream, please visit the breakout sessions, connect with Weifeng, and ask how can you get involved.